Yeah, good evening, everyone. So I'm really happy to be here. I was here, I think, maybe 3-4 years back when I was a TA. And I mean, I've attended these popular science talks before, so a pretty high standard to live up to. So I'm now a data scientist at a company called Sabre. They are an airline company. They provide solutions for airlines. So airlines and agencies. So if you book a ticket and you see something like Make My Trip or something, so Make My Trip actually accesses the database that we have at Sabre, and so that is so sort of you can think of it as a layer between airlines and your actual ticket. And I mean, so it's not only that, they also do a lot of things like crew planning, flight planning, flight scheduling. So a lot of operations research and software solutions as well. But that is where I work now. The team is actually called Sabre Labs, and there we do build some prototypes. So I mainly work in forecasting. So we are trying to, so my job now is actually forecasting market demand. So like, for example, Indigo. So Indigo is one of Sabre's customers. So they come and ask how many people are likely to fly next year, from sort of, let's say from this month to 2023. And then we come up with estimates which should be fairly close to what is the reality. So these are the kind of problems that I work on now. Before that, yeah, my earlier avatar was actually as an engineer. So I was building, so for like now 5G auctions are about to happen, but I worked on 4G technology. So that also had a bit of statistics, not as much as I do now. And then after some years in the industry, I went back to academics. I did a PhD in IIM Bangalore, and that's where I got into forecasting. So today I'm talking about one of my thesis problems. So this is I sort of do something similar even now, but this I thought might be a good topic for all of you, especially if you haven't done time series, if you haven't done any forecasting. So I'm going to get into what forecasting is, what time series is, and what a data scientist is before I get to the actual problem. So just bear with me. So this slide, so you might have heard, I mean, a lot of the buzzword in the industry now is, especially since you're all mathematics students, the jobs are in data science, right? You might have heard, so, and you would have heard like, machine learning, artificial intelligence, and so on. So when Sabre goes out to recruit as well, we look for people who have done projects in this area. So I'm sure you'll all be coming to it fairly quickly. So I just wanted to talk about what is supervised learning and unsupervised learning, because what I work on are supervised learning problems. So if you see, so I mean, basically as a data scientist, my bread and butter is data, right? So you're given a data and you have to tell a story or find some meaning behind it. So in supervised learning, your data has already been categorized, right? There is some structure to the data already. It has labels. It is, you know exactly what the rows and columns are. In unsupervised learning, it is unlabeled data. So basically, you're going in blind. You have to make sense of the data. So, so for supervised learning, things like classification and regression are the things you can do. So you've already labeled the data. So in a data set, you think of it like a matrix, right? Each row is like an entry and the columns are some kind of features for your data. So you're trying to find a relation between the rows and the columns. So you're saying some columns can predict one column better, and basically you know what the columns are, right? Like, so I talked about this airline market. So in an airline market, I might know how many people traveled last year. So I can use that to predict what happened in the future. Or I know that there is a conference happening, for example, this summer school. And then I say that, okay, people flying into Bangalore is going to be up by 100 maybe in the month of June. So these kind of signals are what I'm trying to get from the data, and that is what is supervised learning. So one is when it is numerical, then it is like, that's what we call regression. I don't know if you've all already encountered regression. But then there is also classification, where you're trying to say if it is yes or no, or it might be more categories than yes or no, but you're trying to find groups in the data. But it's all basically labeled data. So that is what we call supervised learning. In unsupervised learning, you just let the computer or the algorithm find the association themselves. So it knows nothing. It just says, oh, these group of points are close together, so they belong to one cluster. And then after you make the clusters, you decide on what they are. So if you come across supervised learning and unsupervised learning, this is what can we get rid of that set up professional audio? Or, I mean, it's okay. So, so this is some more, I mean, I think a visual aid to supervised and unsupervised learning. Yeah. So if you see here, unsupervised, right? So you don't know, there are no colors or something to tell you what the data is, but you just know that these group of points are close together. So you say this is one cluster, this is one cluster. And then in supervised learning, here you know it's already class 1, class 2, and some unknown class. But from there, you're trying to make sense of how they relate to each other. So so an example of, I mean, in an unsupervised learning thing, you also don't know how many. So here they turned out there are 2 clusters, but you may not know. So you let the program learn. And when you know, when it is supervised learning, then classification is when you try and draw this boundary line, right? Your algorithm or the program you write would draw this boundary line and say, the points above the line are green, the ones below are red. So this is what you would try and get from the data. And regression is when you try and find a relationship, right? Like I said, so there is X and Y. So X is your, as usual, the lower axis, and Y is this vertical axis. So you're saying these points have this kind of relation. So you can say Y is equal to mx plus c. You're trying to find m and c. So that is, I mean, it's not a straight line here, but you get the idea, right? So let me give you some examples. I've talked about this thing. So what do you think? I mean, what is fraud detection for credit card companies? These are kind of examples that you would work on as data scientists if you choose to become a data scientist. Fraud detection for credit card companies. So your job is actually to classify it as a fraud or not a fraud. So what do you think it is? Is it supervised or unsupervised learning? Unsupervised. Okay. Social network analysis. I think, Shiva, you do some network analysis here, right? This year, okay. Yeah, so when I was there, we actually did something like how close are your friends or something like that we had done. So that is another problem that you could work on. So here, so like I said here, you're trying to find the nearest neighbors, right? Like, so say one of you're trying to find how many people are close to you in the big group. So that, what do you think that is? I mean, I'll give you the answers in the next slide. Unsupervised. So predicting house property price. So this is like, whenever you do any data science course, you will see this as one of the problems because it's a nice data set. It's been cleaned. And then you have exactly the columns, the relationship, it works out very well. So, but I mean, real life problems, like the problems I work on don't this thing, but you will see sort of a nice example when you're doing these courses. So you probably predict a house property price from various things like, the location, the number of bedrooms it has, how old it is, and whether it's an apartment or a house, or you get all these details. So this is like a regression problem, right, where all these factors and you're trying to find a relation. And then a company wants to adjust its products and offerings according to customers. And then, predicting whether a patient has a disease or not. So this is a typical yes or no answer. And this also, whenever there's a classification problem, you'll see that this is one of the heavily used example, right? Like this is also a nice data set which is available. And then again, analyze survey results to check whether a customer was happy or not. So I would like to say that in Sabre, actually, we work on very, most of these problems we actually work on. So we want to predict customer behavior. We want to predict market demand. We want to classify markets as, luxury, business, normal, those kind of things. Yeah, so these are your answers. This was just to brief introduction into what I do and what a data scientist's job is like. So now I'll get into time series forecasting. So forecasting, the reason I got into it was something like this, because it is sort of nice, right? When you can think that you can predict the future. There are, that astrologers are, not really, there is no science behind it, but you see them doing well. If you remember, like, I don't know when it was, the football, there was this Paul the octopus which could predict the outcome of the football game, right? The FIFA World Cup. There was, you were all probably very young then. But so there's something nice about being able to predict the future, right? But so if there is a crystal ball and you can predict the future, that is what everyone wants, right? Not only in your personal lives, companies want that, everyone wants that. But there are some truths about forecasting. Forecasts are always wrong. There is never like 100% forecast. But what you can control is how much and in what direction, right? Whether you're wrong, you overestimated or underestimated. If you must forecast often. And the most reliable way to forecast the future is to understand the present. So basically, these are all general truths about forecasting, but what it means is understand your data. So once you know your data, then you can actually do a good job with your prediction. So what do we mean by time series, right? So time series means there is generally a time label attached to the data. So these are in R, these are like very old data sets, but they're also sort of the Bible for forecast package. If you load the forecast package, you'll see this quarterly earnings of Johnson & Johnson. And this is just a general thing. But this is how it looks, right? Over time, like I said, it's very old. It's 1960 and up to 1980, they have quarterly earnings. So anytime there is a timestamp attached to the data, then it's called a time series. And like you see, the earnings have been increasing over time. And the ones that you see in blue here is what you're trying to predict. So you have data until something like 1978, and then you're predicting for 4, 5, 6 years after that. Quarters, but yeah, maybe a couple of years. So what we call as a training data is what you use as your, what you use to discover the relationships in the data. That is called training data. And so there is some part which you keep aside where you know the answer, but you use the model that you fitted on the training data on the data that you've kept aside. So that is called the test data. And then you see how well you've done there. So that's what is called a fitted value. When you use the training data, so the orange dots, if you see here, these are what your model says the data is, but your data is actually the blue dots, right? But your model is, so you put some equation to describe the relation between time and the value. And what you get are the orange dots. So this is from, you know the data, you're trying to fit some equation to it, and you got the orange dots. When you go to the point where you've kept the data out, those 2 points here, that is the forecasted value. So you didn't have it, but you're saying that's what it is. So this is, yeah, it's a rough introduction to time series. So there are, this is a whole thing. I mean, I did my thesis on it. So there are a lot of methods. There are qualitative methods as well, which I was, I mean, I did know about it, but it's surprising how much, you know, there is like representative judgment, Delphi techniques, all these where, I mean, there is even an expert opinion. So I thought no one would use that nowadays, because, you know, everything from IPL to things like that, you want the data to speak for you, right? But it turns out that people still rely on expert judgment. So I was surprised to see that. Quantitative methods is where I work. So there are time series projections where you know, you use traditional statistics methods. There are also econometric methods, like I said, the regression model, and then sometimes I heard you did a simulation today, Monte Carlo simulation. So you also do simulations where you try, and you know, if there is something where you don't have enough data, you actually simulate it and then try and find. And then there are artificial neural networks. So all these are some of the forecasting methods. So this is an example. I mean, I picked one where what I'm worked on in the last couple of years. So this is airline market demand forecasting. So if you say Y1 to YT minus 1 is the historical passenger count for a market M, then we want to forecast after T, right? So T to T plus H, where the small h we call as the horizon. So how far ahead you want to predict. So this is the problem which I've been working on. So there is a training set. Like I said, I already have data from Y1 to YT minus 1 for a market M. And I'm looking at monthly data. So monthly passenger count from some particular origin to a destination. And H is the, so it's called a forecasting horizon. It just means the test period, right? For which I don't have data. And to give you an example again, this is how it looks, right? This is a table. So PAX is passenger. And for Jan 2010, there were 46,000 passengers. So this is for a particular market. It could be something like Dallas to San Francisco or something. I mean, I'm not sure where I picked it from. But you have everything. So you have from 2010 all the way up to 2015, and you want to predict for Jan 2016. So that is your problem. So we saw what a time series is, but what you can do is actually decompose the time series, right? You can break it down into, your full data looks like the first panel here. So this is San Francisco to Los Angeles. And it looks something like this. But what you can do is, so this is it's a very old time series technique where you decompose it into the three things that you see below. So there is one part where you're only extracting the seasonality. So what we mean by seasonality is exactly what you think, right? It repeats every so often. So here, this is something which we are seeing, which every year there is one pattern like this, right? So it peaks, I think, around December when the travel is high in the US. But it's sort of low maybe in February or so. So you see this pattern repeating year after year, and like you see, all of them are at the same height. So this is just saying that the data is very seasonal. This trend is so like you saw in the Johnson & Johnson thing, right? Where it's climbing up. So that is what you called a trend. So this is what we do. So you break down the time series into a seasonal part, a trend part, and whatever is the remainder. If your remainder still looks like, you can see it sort of looks still seasonal, right? So it should look very noisy. If you broken it down like this and you still have some signal there, that means you're not doing the best you can. So these are all visual tricks you can do to see how it looks. So these are all like popular methods. The naive method is, like I said, I mean, I would just use the previous year's travel history and say, this is what happens in the following year. there is a method called ARIMA. I won't go too much into it. I'm just listing it here. And then if you get into machine learning and all that, then you will definitely be doing some sort of boosted trees. So that's why I put this in here. I'll talk a little bit about what it is. So yeah, this is the naive method. So like I've plotted the yearly travel, travel for 2010 to 2017. And you can see it's fairly, I mean, at least in August to September, you can see they're all very similar, right? It's just that the number of passengers has been increasing year on year, but there is definitely heavily seasonal. So this is another way of looking at the same data. And again, it shows you that it's very seasonal because you're getting the same pattern year on year, right? So, so this is not a bad method, right? You can use it as a benchmark. You can say that, so suppose I want to predict T plus H, I would just use 12 months earlier to say that is a number who are going to fly. Yeah. Second plot. Huh? It's just a circular plot of the same thing. So it's the same passenger count. But if you see, it is, January, February, March, they are in a circle rather than a straight line. So it's basically like I've rolled this up, just a different way of looking at it. But it sort of brings out the seasonality because if you see September, there are all these edges aligned. August, not so, I mean, August also it's there. July, not so much, but June, you can see that they all align. March is pretty clear, December is clear. So just a way of checking. Yeah, sort of like 11. So this is again a very, I mean, it's a very, very old method, maybe 100 years old, but it's still widely used. And it's called autoregressive integrated moving average. You need to get into a little bit what we mean by autoregressive moving average. You probably know, right? I mean, it is what it is. Autoregressive is like how much of the past data can you connect, right? Like, so I can say T is some alpha times T minus 1 and alpha 2 times T minus 2 and so on. Like, so you keep going back. So that is what this is showing. So y of t is actually phi 1 of y of t minus 1 and phi p of y of t minus p. But after that, these coefficients start losing significance. The errors are sort of average. So the thetas are on the errors and the phis are on the y's. So the p and the q are, so the p is the order of the autoregressive part because p is the point where your signal is still strong, that you use it to model y of t. And q is again error where it is still used to model y of t. So these are all things that you should know if you're using this method. And again, these methods work very well when you have seasonal data. If there is no seasonality, then this will not do a very good job. Again, there is an R package called Forecast, which is quite, I mean, it's very good for time series. It's written by one of Monash University's Rob Hindman. So he's sort of pioneered a lot of things. So this auto-ARIMA, it tries and finds the P and Q by an iterative method, and it's very fast. It's also, it also gives you a reasonable accuracy. So you don't have to actually know what's going on. If you just call auto-ARIMA on your time series, it will fit a model and give you the model back. So that's a magic of R. So this is what, these are more modern methods, XGBoost. I mean, even this is probably like now 20 years old, I think. So these, I think, this one, I think came out of Microsoft. So these are tree-based approaches to fit your model. Don't worry about the text. So what happens is, so you put one model, right? Like take something very simple, like I said, y equal to mx plus c, and then you see what the error is from that model. Then you sort of increase it, add one more x1, x2 to it, and then see what happens. If your error continues to decrease, then you keep adding more and more branches and leaves. But at a point where the error no longer decreases, you stop. So it's sort of yeah, so yeah, I mean, if you've gone through gradients and all that, then you'll probably understand this. So you're optimizing a curve, you're moving along a gradient, and there is a point where you can no longer optimize, and that's the point where you stop. So this is actually extremely popular. If you know about Kaggle competitions, so if you have any aspirations to be a data scientist, you should follow it. So there are these competitions which happen, and most Kaggle grandmasters actually they use some variant of XGBoost. Yeah, well, this is the problem that I worked on for my thesis. This is electricity load forecasting. It's not a very exciting topic because, I mean, electricity load, I mean, we all, it's getting more and more important. There are, cars which are electric now. So we do need electricity, and I mean, your phones, the batteries still need to be charged every day, especially if it is a fairly advanced phone. So electricity is important. It's a sort of hot topic. But the thing is, electricity load forecasting by itself, we've reached a fairly high level of accuracy. I mean, it's very, very difficult to beat the level of accuracy because it's so predictable, right? In any city, you want to predict the electricity demand, you pretty much know how many watts are going to be consumed. So why did I pick this? Because I'll tell you. So what happened is when we looked at, so it came from my advisor, they came with a data set which was electricity load. And they said that there was a method which the person that I told you, Rob Hindman, he had a package. And it did a fairly good job, and they wanted to see if we could do a better job than that. So that's why I started looking at the data, and then it was fairly interesting actually. So what we found is electricity load has actually multiple levels of seasonality. So the one that I showed you had only yearly, where every month sort of, so January 2010 and January 2011 and so on. So they are all aligned, but this data had multiple levels. And the data was huge. I mean, because it is recorded every 5 minutes and it goes all the way back to 2008 or so. So we had fairly large amount of data to analyze. So, these kind of problems, right? Electricity load or mobile network usage, there is a lot of data. It's recorded very frequently, every 5 minutes or every hourly. So you can get a lot of insights from the data. But the problem is like I showed you ARIMA and some traditional methods like exponential smoothing. So those kind of things, they can't deal with seasonality at multiple levels. And even if it is longer, so if it is monthly or daily seasonality, then ARIMA works very well. But if it is yearly and you have only about 5-6 years of data, then it's not, it can't handle it. So this was what this company came to us with. So they said this method is there. This is an acronym. Again, it means trigonometric Box-Cox transform. A stands for ARIMA, trigonometric series, and so on. So don't worry about that. But it's just a method like ARIMA. It's think of it as a black box. You give it a time series and you want to make projections. So that was our problem. We wanted to see if we can do better than TBATS. So we recorded, we have data which is recorded every 5 minutes, which means it's 288 observations per day. So if it is for 10 years, you can imagine how big it is. So 288 into 365 and then into 10, right? So it's a lot of data. I mean, not as much as maybe, YouTube or, all these video and image things, but yeah, for a normal data set, it is quite big. We use so typically electricity load uses these, so it's called wet bulb and dry bulb temperature. So dry bulb is exactly what you think when you want to measure the atmospheric temperature. It is a completely dry bulb. And so what you see is actually the atmospheric temperature. A wet bulb is actually when, they sort of soak it in wet swabs. And so the temperature is lower than a dry bulb, but you get a sense of sort of the humidity and how, so these are fairly helpful covariates. So wet bulb, to give you an idea, if wet bulb temperature is more than 35 degrees Celsius, then human life is not possible. So it's very hot actually. So for us, we use data from September 5th, 2008 to 2015 and kept, so we are forecasting 1 year ahead. So it's from March 2015 to 2016. So this is how the data looks like. This is just, I just picked 4 years for a snapshot. So again, if you see like the earlier one, right, it's very, very seasonal. So you can see, so this is New York data. So you can see that in the summer months, actually, there's a lot of electricity where they're using more air conditioners and all that. And you can see in 2009, it's high, in 2010, it's high, 2011. And then in the winter months, like between January to March and December, November and all, it's sort of much lower because I think they use gas heaters and not electric heaters, right? So this is an example of annual seasonality. And then if you look, this is weekly seasonality, right? Where you can see that the first two, where it's a lower electricity load, these are the weekend. So it says week starting on Saturday. So Saturday, Sunday, and then it's like Monday through Friday. And then similar, so this is a week in February, this is a week in July and August. And you can see that it's fairly, so yeah, in July it's higher, like you can see the peak consumption was like 11,000, but the pattern is there, right? So what I want to emphasize is the seasonality. So you saw annual seasonality, there is weekly seasonality, and then this is daily seasonality, where within a day, right? So you can see that the consumption is the lowest around like 4 in the morning, keeps increasing, and then reaches a peak around 4 p.m. and then starts dropping again. And any day you pick, you can see this pattern. So these are again 4 different days. So yeah, so what we did was actually leverage this sort of multiple seasonalities, which methods like ARIMA and all don't do. And yeah, so this is again, I mean, it's all weather related, but basically our mathematical methods can take. So this is the work that I did. So this is a 2-stage method where we sort of separate the processing, the modeling, like the training period which I showed you, into 2 parts, right? So in the first part, what we do is, so we have 5-minute data, which is fairly frequent. So what I did was aggregate it to a daily level or a monthly level or something like that. Okay, the reason why you didn't see monthly was because I mean, months, it's difficult to model monthly seasonality because different months have different number of days. So typically in a time series forecast, you will not see monthly seasonality unless people have done something I mean, specific to their problem. So what we do is actually, so there are, the seasonality can be additive or multiplicative. So what you do is try both. And then first thing you do is sort of aggregate all the, so you aggregate all the 5 months, get one value for the daily level. And then you put all your modeling on the averaged signal. You estimate seasonality, which is what I called S here, S high, from, so from both, right? You do, this is additive seasonality and this is multiplicative seasonality. So what you're doing is actually separating this average signal from the real signal, but you're working with 5-minute data here. So then you estimate seasonality from there and then finally combine the way, so if you did a subtraction here, you would add the seasonality to the estimate here. If you divide it, you would multiply. So it's, I mean, it's not very complicated. The only thing is you have to keep track of what sort of aggregation you did. Yeah. Yeah, so what we do is we do everything, like do both additive, multiplicative, which is, I think, a way in which data science has been going. So yeah, you do both, and you also, even for the aggregation level, right? I don't know which one to choose. I don't know if I should aggregate it hourly or daily or whatever. So I do that as well. So I'll have multiple tracks, and then I choose the one which gives me the best performance. Sorry? Yeah. Yeah, no, so if I aggregate it to a daily level, sorry? Yeah. So I am losing information if I only work with the aggregated signal. But what I do is I'm extracting seasonality from the full signal. So it's not like I'm throwing away the data. So I do both. Yeah. So, and then you do everything possible and then finally find which one gives you the least error. So that is a way of deciding. So for the Y low, right, the aggregated signal, we pretty much try everything. We tried TBATS, ARIMA. So there is an ARIMA with external regressors, which is where, so the regressors are these temperature variables. And then you just do a plain regression. So like I said, the residuals are the leftover signal, right? After you fitted your model, the leftover signal. That's called a residual. So on the residual, you again fit a model, because if there is something you left out which you didn't capture, you want to capture it. So these are all, I mean, these are standard techniques. I'm not doing anything fancy here. So then of all these, you choose the best model and then you make a prediction. But this is still your aggregated signal. Like you said, we might be missing some information which we threw out. Yeah, so for the regression, these are the sort of things, right? Like we have a day number, we have maximum and minimum dry bulb and wet bulb temperatures. And then these dummy variables are something you'll learn when you do regression, because see, typically if it's a numerical value, you can just put it in like as it is. But if it's not a numerical value, for example, if it's, you know that if it's a Saturday or a Sunday, it's a different signal than if it is a weekday. So how do you let the computer know that, you know, you have to take this into account? You can't say Saturday, Sunday and things like that. So that's where this dummy variables come in. So you sort of codify it, like you, I mean, you can even think of it like numbers, right? Like 0 to 6 or 1 to 7 and so on. So then your algorithm has a chance of making sense, whether it is so if one is Saturday and two is Sunday, then it might be able to see some patterns, like say that Saturday and Sunday it's lower than the rest. So these are the things. And then so like I said, then we use the error to make the decision, right, on which model to pick, because we are basically throwing the kitchen sink at it, say do everything, right? So these are some error metrics. You can concentrate on this MAPE, which is mean absolute percentage error. It's nothing fancy. It's just A is the actual signal. So it's like the passenger count, if you remember. So A is the actual passenger count and F is your forecast. So the difference between that is your error. Now when you divide it by your actual, you get a percentage error. And you don't care whether it's an overestimation or an underestimation. So that's why you do an absolute value. And then you find the average over all the values that you had. So I use the MAPE and I pick the method with the lowest MAPE. So that I say that will be the error, right? These are other, you'll see this RMSE or RMSPE. These are methods which come with your forecasting packages now. So whenever you fit a model, it will give you all these values. So if you look at MAPE or RMSE, what it means is it's a way of, so root mean square error, root mean square percentage error. So you have to, the lower the error, the better the method. So these are some of my results. Like I showed you with all the, this is the stage 1, right, where I have an aggregated signal. These are mean square error, mean absolute deviation. So look at the last column because it gives you a sense of what is happening. So if you see, it's quite small. Like I said, I mean, even now in all electricity load forecasting competitions, the error is typically 2%. It's like really good. because in the airline industry, we get errors like, in 10%, 15%, sometimes 30%. So those problems are really difficult to forecast, but electricity load is actually, you can do a fairly good job. So like I said, we have various methods, and then we'll pick. So based on the model period, we'll say probably regression and TBATS on residuals was the best one. So we'll use that for our future. But if you look at how it did in the holdout period, then it was actually TBATS with weekly and annual seasonality. So it wasn't this one, but this. So so that's why we always have a holdout period, because you don't want to overfit or yeah, I haven't talked about that, but basically you can do a very good job in the training period, but then when you get new data, your model completely falls apart. So that's why you keep out something, you see how it does, and then you choose your what method you want based on that. So holdout is, so you have data, like I said, suppose you have from 2010 to 2015, you keep 2015 out of the modeling. So that is why it's called holdout or a test period or something. So you get your model from 2010 to 2015, and then you apply it to the data in 2016. And that is the error there is what is the holdout period error. So again, seasonality is additive and multiplicative, and in additive, there are various ways in which, so seasonality is something, I mean, it's just like fitting a curve to this thing. So that's why you see polynomial, there is spline, there are trigonometric methods, there is a classical method, which is just some sort of averaging. And so we have both for the additive and the multiplicative thing. So now we've gone back to the 5-minute series. We find the seasonality from there. Yeah, so then finally, we combine both stage 1 and stage 2. So we pick the 2-level TBATS for stage 1. For stage 2, we apply all the possible seasonal variations. And so if you can see the bolded part, the best one was the multiplicative plus the 2-level TBATS, and we got an error of 6.75. Whereas TBATS, which was why we took up this problem in the first place, the 3-level TBATS actually gives 15%. But if you look at the model period, right, TBATS was so good, it was like 0.28. So it is practically like, I mean, I said right in the beginning, there is no perfect forecast, right? But this was practically perfect because 0.28% error is fantastic. Yeah, so this comes from overfitting, right? It's like, so suppose you have a curve like this. If you find a model which fits each and every point, then your new data, if it is flat, this is not going to work. So that's what happened. Yeah, so this is the end of this problem. So basically, the 2-stage framework that we proposed is sort of more efficient than the TBATS. It doesn't suffer from overfitting. We are able to use covariates, which TBATS doesn't do. And it's also fairly faster than TBATS because of the aggregated data. It actually it has less data to fit. So yeah, before I finish, I just want to talk about R for forecasting. I mean, I pretty much in my for my thesis, for my entire PhD, I used only R. Actually, I've been doing more of Python since I joined Sabre. But for forecasting, actually R is fantastic because all the statisticians who worked on these like these forecast packages, all of them worked with R. So the R packages came from that stable, and Python actually was people were trying to reproduce what R does. So, and I think frankly people don't really care. So if you look at ARIMA in R versus ARIMA in Python, it's much slower. It's also less accurate, but no one has bothered to sort of update it because I think most of the work in forecasting is still done in academia. But what I want to emphasize is, so during my PhD, I actually built a package for this method, this 2-stage method, and this building a package for your work, if you work in R, and I think you will, it's very easy, right? So this is a tweet by this guy, which sort of went viral in 2015. Like, I wish I'd left this code across starter.r files instead of combining it into a package, said no one ever. So what he means is, I mean, when you work, right, you keep creating new files for each function that you do. And then finally you're searching like, oh, I wrote that function, then I wrote this function. But it's actually quite easy to create a package. And once you do that, you can use your own code. So, and it's actually as easy as 1, 2, 3. There is the ggplot. I don't know if you guys have gone over it. So the ggplot author, Hadley Wickham, is the one who wrote. He's made this very simple actually. So he has a book which. So the first one is my package. It's available on GitHub. So if you do, instead of you doing install.packages, you can do GitHub install and this one, and you'll actually get my package. I mean, if you just install DevTools and Roxygen, you can actually build your own package. So I'm just giving you a small example here. Suppose you just have a couple of functions, right, which convert a temperature from Fahrenheit to Celsius, or Celsius to Fahrenheit. You can make a package around this. I mean, it's not needed, but I'm just saying when you do more, like for example, if you're building a Monte Carlo simulation, certainly you should write a package for it, and it's very easy. So what you should do is you create a package, like you can say my R package or something, put your file there, which is essentially all your R files there. And then you need a descriptor. So you'll have a description file. So once you install this, it actually gives you the template as well. So you don't have to do anything. There is a description file. You just open it up, you name your package, you call it a package, you say a title and then your version. And that's it. You just say library dev tools, load all, and all your functions will be there. And once you put it on GitHub, someone else, like suppose you want to share it, that person can say GitHub install. You tell them your package name and they'll be able to do it. So yeah, and then, I mean, you can just run this and see. I think this one I picked off someone. So there are lots of tutorials and all of them are pretty much the same 1, 2, 3 steps, but you can try this. So I would recommend creating your own package whenever you're working. For time series, there are, so forecast was what I used. There are also, you can combine different forecasts. So suppose you have 10 methods. So one method would do well in 1 year, another method would do well in another year. So actually combining them together is, it's actually the one which wins competitions. So there is a forecast combination package. I didn't put it here, but forecast is like sort of the bread and butter if you want to do time series forecasting. Profit came like XGBoost came from Microsoft. Profit came from Facebook. This is also a very popular package. So this is good. Fable is if you don't have any covariates, like for example, the market size forecast which I showed you, it has only historical passenger. So for those kind of things, Fable is good. And if you go to CRAN packages and you want to do some core time series forecasting, these are some of the packages that you can use. So you can just install them. If you have a time series, just give it as an input and you will find you're able to do your own forecasting. Yeah, and lastly, I mean, so I'm part of this group called Our Ladies Bangalore. So there is an Our Ladies group, which is a global group. So they are like it says here, it's a worldwide organization which wants to promote gender diversity. And so actually R is a very welcoming community. If you see even people like Hadley Wickham, he gives talks in Our Ladies groups. There are they meet. I mean, it depends on how active your chapter is. I mean, we are here, but they also have like people who actually are package authors come and give talks, and very inclusive. And even those people say that they always Google for code and so on. So any of these chapters, you can, even their past talks, you can go and pull it up and view it. So it's a very nice community to be part of. So in Bangalore, the 4 of us started. It was Aditi, me, Deepthi, and Soumya, who started this Our Ladies Bangalore chapter. Neeta joined us maybe 6 months later. So all my other co-organizers, they all work in sort of air quality forecasting, air quality indication sort of thing. But this is also a nice group. So if you want to be part of it, send me an email. I forgot to put my, but you can email bangalore@ourladies.org as well. So what we try to do is have a monthly talk where we invite, depending on the interest. So it's usually driven by the four of us, what we want to learn, what we want to use R for. And because most of them are air quality people, we sort of look at, spatial R and stuff like that. But there have also been, so we've had Shiva speak once about his, I don't know if you've seen his COVID website, but it was a nice talk. Then we've had about deep layer and tidy models and so on. So it's a good thing. On Twitter, we are not very active, but whenever there is a talk, we put out the information, the poster and everything. So we have gotten people, especially if it is something like, visualization or I think there was one, so building maps with our, there was some person who works in conservation and ecology and all that. So when he spoke, we had quite a few, we had about 40 people attending. So it's a nice group. We always welcome more people. So if you want to join, send us an email. That's it. So any questions?